If you spend any time in cryptocurrency communities, you have almost certainly encountered the question. Someone posts it on a forum, or a journalist raises it in an article, or a concerned investor brings it up in conversation. The question is this: will quantum computers break Bitcoin? And depending on who you ask, the answer ranges from absolutely, and it's going to happen soon, to never, stop worrying about it. Neither of those answers is correct. The truth sits in a more complicated, more interesting, and more honest place, and that is exactly where we are going today. We are going to look carefully at what quantum computers could theoretically do to Bitcoin and blockchain technology, what the actual timeline looks like based on where quantum hardware stands right now, and what the cryptocurrency world is doing, or arguably not doing enough of, to prepare. To understand the threat, you first need to understand what is actually protecting Bitcoin. Bitcoin security rests on two pillars of cryptography. The first is called SHA-256, a cryptographic hash function used in Bitcoin's proof-of-work mining process. The second, and more directly relevant to this discussion, is elliptic curve cryptography, specifically a scheme called ECDSA, the elliptic curve digital signature algorithm. When you own Bitcoin, what you actually own is a private key, a secret number, and a corresponding public key that is mathematically derived from it. Your public key, or a hash of it, is your Bitcoin address. When you want to send Bitcoin, you use your private key to create a digital signature that proves you authorize the transaction without ever revealing the private key itself. The security of this system depends on a mathematical problem. Given a public key, it is computationally infeasible for a classical computer to work backward and figure out the private key. This is the elliptic curve discrete logarithm problem, and classical computers cannot crack it in any reasonable amount of time. Here is where quantum computing enters the picture. In 1994, mathematician Peter Shor published a quantum algorithm, now universally known as Shor's algorithm, that can solve certain mathematical problems, including the discrete logarithm problem and integer factorization, exponentially faster than any known classical algorithm. In theory, a sufficiently powerful quantum computer running Shor's algorithm could take a Bitcoin public key and derive the private key from it. If that were possible, an attacker could steal Bitcoin from any address whose public key has been exposed on the blockchain. And here is an important detail that many people do not realize. Your public key is exposed every time you make a transaction. Bitcoin addresses are hashes of public keys, which provides a layer of protection. But once you spend from an address, your public key becomes visible on the public blockchain. Addresses that have been used to send transactions are potentially more vulnerable than addresses that have only ever received funds and never spent them. So is this a real threat? Yes, in principle. Is it an imminent threat? Based on everything we know about the current state of quantum hardware, no. And the gap between theory and reality here is vast. To run Shor's algorithm against Bitcoin's elliptic curve cryptography at the scale required to actually break it, current estimates suggest you would need a fault-tolerant quantum computer with somewhere in the range of 1 million to 4 million high-quality logical qubits. These are error-corrected logical qubits, not the raw, noisy physical qubits that today's machines use. The best quantum computers in the world today have a few hundred to a few thousand physical qubits, and the overhead required to convert noisy physical qubits into reliable logical qubits through error correction is enormous. We are talking about needing potentially thousands of physical qubits to produce a single reliable logical qubit, depending on the error rates and the error correction scheme being used. The honest assessment shared by most quantum computing researchers is that a machine capable of breaking Bitcoin's cryptography is likely, at minimum, a decade away, and quite plausibly, several decades away. Nobody can say for certain, but claims that this threat is imminent are not well supported by the current evidence. What about the SHA-256 hash function used in Bitcoin mining? This is actually considered more robust against quantum attacks. The best-known quantum attack on hash functions uses something called Grover's algorithm, which provides a quadratic speed-up, meaning it effectively halves the number of bits of security. SHA-256 has 256 bits of security classically. Grover's algorithm would reduce that to roughly 128 bits of effective quantum security. That is still considered very strong, and most cryptographers believe SHA-256 would remain secure even in a world with large-scale quantum computers, or could be straightforwardly upgraded if needed. Now let us talk about what the cryptocurrency world is actually doing about all of this. The picture here is mixed. On one hand, there is awareness. Researchers and developers in the blockchain space have been discussing post-quantum cryptography for years. The National Institute of Standards and Technology, NIST, finalized its first set of post-quantum cryptographic standards in 2024, providing the cryptographic community with quantum-resistant algorithms that could, in theory, replace the elliptic curve cryptography that Bitcoin currently relies on. These algorithms are based on mathematical problems, such as lattice problems, that are believed to be hard for both classical and quantum computers. On the other hand, actually upgrading Bitcoin's cryptography is a different matter entirely. Bitcoin is a decentralized network with no central authority. Any fundamental change to its cryptographic foundations would require consensus among a globally distributed community of developers, miners, and node operators. The governance challenges involved are immense, and the technical complexity of a migration of this scale should not be underestimated. There is also a category of existing Bitcoin that is particularly exposed. Early Bitcoin, including coins that are widely believed to belong to Bitcoin's pseudonymous creator, Satoshi Nakamoto, was stored in what are called pay-to-public key outputs, where the public key is directly embedded in the blockchain rather than hashed. These addresses are already fully exposed, meaning if a quantum computer capable of running Shor's algorithm at scale ever existed, those coins would be among the first at risk. Estimates suggest that roughly 1 to 2 million Bitcoin, worth hundreds of billions of dollars at current prices, sit in addresses with directly exposed public keys. The bottom line is this: quantum computers do represent a genuine, long-term cryptographic threat to Bitcoin and to much of the security infrastructure of the modern internet. That threat is real. It is taken seriously by serious people. And the work to develop quantum-resistant cryptographic standards is already well underway. But the timeline for this threat to become actionable is almost certainly measured in years to decades, not months. The responsible course of action is steady, methodical preparation, not panic, and not dismissal. The quantum threat to blockchain is a slow-moving storm that we can see coming from a long way off. The question is whether the decentralized, consensus-driven world of cryptocurrency will move fast enough to get out of its way.